Hello and welcome to our third session of the chapter Electric Charges and Field. This is the first chapter of our 12th physics. In this session, we will discuss Coulomb's law. I have divided this Coulomb's law into two parts. This is the first part of the Coulomb's law. In this video, we will discuss the definition of 1 Coulomb, Coulomb's law in vector form, and what is its significance? What is the importance of Coulomb's law in vector form? What is the limitation of Coulomb's law? And finally, what is principle of superposition? So let's begin our session. First, what is Coulomb's law? So Coulomb was a great physicist who measured the force between 2-point charges, and he found out that the force between two charges varied inversely as the square of distance between the charges. Suppose we have two charges here. Suppose I'll denote first charge by Q1 and second charge by Q2. If the distance between these two charges is R, then the force between these two charges varies inversely to the square of distance between these two charges. Also, the force was directly proportional to the product of magnitude of the two charges. The force was proportional to the product of magnitude of the two charges. The third point which he observed that the charges act along the line joining the two centers. Means suppose both of them are positive charges, then the force will be repulsive. The force on Q2 due to Q1 will act along the line joining 1 and 2. Similarly, the force on 1 due to 2 will also be repulsive. It will also act along the line joining Q1 and Q2. So, Coulomb found out that the force between two charges is directly proportional to the product of the magnitude of the charges. Means bigger the charge, bigger will be the force of attraction or repulsion. Also, greater as the distance between the charge increases, the force decreases, and it varies as inverse square law. The third point which he concluded that the force of attraction or repulsion between the two charges will act along the line joining the two charges. So finally, combining both these two, he concluded that F is proportional to Q1 Q2 upon R square. Now, removing the proportionality sign, a constant appears K. It is K Q1 Q2 upon R square. So here the value of K is 1 by 4 pi epsilon naught. This is called epsilon naught, and its value has been calculated as 9 into 10 power 9 Newton. The epsilon naught is called permittivity of the free space. We will discuss this topic in our next session, what is meant by permittivity of free space. For now, we will just remember its value. The value of epsilon naught in SI unit is 8.854 into 10 raised to power minus 12 Coulomb square per Newton per meter square. Now there is a very important note which we must keep in our mind. Suppose the charge on a metallic sphere is Q. Suppose I have a metallic sphere and on it the charge is Q. Now if the sphere is put in contact with an identical uncharged sphere, suppose I have another sphere which is uncharged, and I bring these two in contact. So this I'll name it. This is sphere 1 and this is sphere 2. So I have brought both of these spheres in contact with each other. The charge on first sphere is Q while the other sphere is uncharged. Now both of the sphere are identical, means both of them will have same mass and both of them will be identical to each other, same mass, same shape, everything is same. The only difference is that the first sphere has a charge Q while the other sphere is uncharged. Now we have brought them into contact. After, when we will remove these two spheres, then there will be a redistribution of charge. I'll repeat, there will be a redistribution of charge. There will be a redistribution of charge. The charge will get redistributed on both of them. Since both of them are identical, so the charge on both of them will become Q by 2 and Q by 2. This is a very important point. We will be using this in a lot of numericals, so you must remember that whenever two bodies are brought in contact with each other, if they are identical, the charges gets redistributed. I hope this part will be clear. Um, Let me ask a question here. Let me put up a question here. Suppose now the second sphere, it has a charge of Q by 2, and suppose if it is brought in contact with a third sphere which has a charge of Q. Now if both of them are brought in contact with each other, then what will happen? So I hope you have understood the question. The question is, just we saw there was a redistribution of charge in first case. Now the question, I have extended the question. The question is, suppose the second sphere is brought in contact with the third sphere. Third sphere has a charge Q. Then what will happen? So after redistribution, now one thing to be mentioned is that again the third sphere is also identical to the second one. Fine. There is only a difference of charge between both the spheres. So after redistribution, the charge on each of them will be half of the total charge. This is how it is redistributed. Charge on each. It is half of the total charge. So I'll calculate it. Half of Q by 2 plus Q. So it is half of 3Q by 2. So finally it is 3Q by 4. So after redistribution, the charge on each will be 3Q by 4. I hope this concept is now clear. I am again telling this redistribution of charge concept is very important. Please revise it and go through it again and again. So our next topic is 1 Coulomb. So now we will define what is 1 Coulomb. So by Coulomb's law, we have already studied that the force between two charges is equal to K Q1 Q2 upon R square. So if suppose we put the value of Q1 and Q2 as 1 Coulomb, we take both the charges equal to 1 Coulomb, and suppose the distance between the two charges is 1 meter. So these are two charges. Q1 is also 1 Coulomb, Q2 is also 1 Coulomb, and suppose the distance between these two is 1 meter. R is 1 meter. Then in that case, putting the values, we get F is equals to K 1 into 1 upon 1 square. So it is F is equals to K. We already know that the value of K is 9 into 10 power 9 Newton. that I have already told you um, in the previous slide, that the value of K is 9 into 10 power 9 Newton. So putting it here, the force between two charges is 9 into 10 power 9 Newton. So we see that if the charges are of 1 coulomb each, kept at a distance of 1 meter, then they will experience a force of 9 into 10 power 9 Newton. So I'll put it again. 1 coulomb is the charge that, when placed at a distance of 1 meter from another charge of same magnitude in vacuum, experiences an electrical force of repulsion of magnitude 9 into 10 power 9 Newton. Means if both of the charge have same sign, they will experience a force of repulsion. If they will be of opposite sign, they will experience a force of attraction. But the magnitude of force will be same, that is 9 into 10 power 9 Newton. Thus, we have defined 1 coulomb. I'll say it again. 1 coulomb is the value of charges which, when put at a distance of 1 meter from each other, then they will experience a force of 9 into 10 power 9 Newton. The force will be repulsive or attractive, that depends on the nature of both the charges. Our next topic is Coulomb's law in vector form. This is a very important topic. Now suppose we have a system of two charges. The first one is plus q1 and the second one is plus q2. Both of the charges are same identical in nature, plus q1 and plus q2. Now this q1 will experience a repulsive force which we will denote by F12. F12 stands for force experienced by 1 due to 2. Similarly, this charge 2 will also experience a repulsive force which we will denote as F21. 21 means force on 2 due to 1. So I'll repeat it again. The force experienced by 1 due to 2 is represented as F12, and the force experienced by 2 due to 1 is represented as F21. So R21 is a unit vector in the direction of 1 to 2. Remember, R21, so it is a unit vector in a direction of 1 to 2. Similarly, R12 is a unit vector in the direction of 2 to 1. So as shown in the figure, we are considering two positive charges Q1 and Q2, which are placed in vacuum at a distance r from each other. So in vector form, we can express Coulomb law as F21. So there will be a vector sign here. F21 is equals to 1 by 4 pi epsilon naught, which is the value of K, Q1 Q2 upon R square, because the separation between the mode of them is R square, and this force is acting along R21. Force experienced F21 is force on charge 2 due to 1. We are talking about here, force here. Force on 2 due to 1. It will be in the direction of R21. It will be in this direction. Means it will move from, the direction is 1 to 2. It is R21. Similarly, the force on charge 1 due to 2, we are talking about this force here. Force on 1 due to 2 will act in this direction. So this is from 2 to 1. So we will write it R12. So it will act along R12, where R12 is a unit vector in the direction from Q2 to Q1. So I hope this is clear. This is the vector form of Coulomb's law. Our next topic is Significance of vector form of Coulomb's law. What does the Coulomb's law vector form of Coulomb's law signify? What is its importance? So the Coulomb's law, the equation which we just saw, it is valid for any sign of Q1 and Q2, whether it is positive or negative. So if the sign Q1 and Q2 are of same sign, means if they are like charges, then F21 is along R21. Look here, if Q1 and Q2 are of same sign, in that case the product Q1 Q2 will be greater than 0. It is for same charges, same sign. We are talking about like charges here. So if Q1 Q2 are like charges, then the product of both will be a positive value, will be greater than 0. In that case there will be a repulsive force. So F21 will act, see, the force on 2 due to 1 will act along R21 So yeah, if this is a repulsive force, then F21 will act in this direction, and if Q1 and Q2 are of opposite sign, here it is they are of opposite sign. So they are unlike charges, so the force, the product of charges will be negative because one is positive, one is negative, so the value will be less than 0. Then in that case, it will be along R12, which denotes attractive forces for unlike charges. So we do not have to write separate equation in both the cases. Just same equation will be valid. Just we will change the unit vector, and same equation will be valid for both of cases, for like charges as well as for unlike charges. The second one is that just we saw here, that is F21 is equals to this magnitude is same, R21 the direction is along R21, and F12 the direction of F12 is along R12. Now we know that R21 and R12, they are opposite unit vectors, they are in opposite direction. So R21 and R12, they are in unit vector in opposite direction, so they can be written as R21 is equals to minus of R12. So if the unit vectors are opposite, then as it can be seen from the equation, the magnitude is equal, 1 by 4 pi epsilon naught Q1 Q2 upon R square. So if the unit vector are opposite, then both of them will cancel out each other. Then F21 will be equal and opposite to F12. It means that the two charges exert equal and opposite force on each other. So we can say that the Coulomb's law also obeys Newton's third law of motion. So our next topic is limitation of Coulomb's law. So what are the limitations of Coulomb's law? What are the conditions where Coulomb's law is not valid? So we have three conditions under which Coulomb's law is not valid. The first is Coulomb's law is only valid when the electric charges are at rest. Second, the electric charges must be point charges. What do we mean by point charges here? Point charges means that the size of the charged bodies should be very small as compared to the distance between them. Only then we can consider them as point charges, and Coulomb's law is applicable only for point charges. Third, the separation between the charges must be greater than the nuclear size. Why? Because for separation less than that, the strong nuclear force will dominate over the electrostatic force. Later on in the syllabus, we will study about a strong nuclear force. A strong nuclear force is basically the force which holds two protons inside a nucleus. So you must be thinking that inside a nucleus, how can protons which have same force, same charges, so they have repulsive force acting between them. So what causes these protons to uh, be to be present inside the nucleus. What holds them? Since if we go through the concept of electrostatic force, then there would be a repulsion, force of repulsion, but still they are present inside the nucleus. So the reason is that there is a strong nuclear force acting between them, which overcomes the electrostatic force, and so they are present inside the nucleus. They remain inside the nucleus. So a third limitation is that the separation between the charges must be greater than the nuclear size. Why? Because for separation less than that, the strong nuclear force will dominate over the electrostatic force. So we have three limitations. We have three conditions under which Coulomb's law is not valid.